So like I said, with right triangles, it's the SOHCAHTOA stuff where you have a right triangle. Each triangle has 3 sides, and it corresponds to different angles within that triangle. There has to be a right angle within the triangle in order for it to be a right triangle, which would make sense. But like I said, what we've talked about in the past has just been the 3 main trig functions, sine, cosine, and tangent, but there's actually several other trig functions, so we're going to add 3 more of those today. Okay, so this first slide is just a couple of definitions. So what trigonometry means is it's triangle measures. So typically when we're working with trigonometry, we typically work with triangles, all types of triangles. And eventually we'll actually talk about how you can apply triangles to circles. So there's actually some circles that we'll work with trig. But again, ultimately it's kind of based off the triangle stuff. So then we use side measurements and a reference angle. And what we like to do, since there's going to be so many different variables and different things like that, what we typically do in upper level math is we switch and start calling angles a different alphabet. Okay. So we typically leave sides as our normal English alphabet, but to kind of help distinguish whether we're talking about a side or an angle, we actually start switching and using some Greek letters for our angle measurements. So with our angle measurement, typically I use the Greek letter theta, which is like a 0 with a little line through the middle. But that's typically what I use to reference my angles. I pulled some problems from the book. They like to use other Greek letters too. So you might see some alphas and betas and zetas and all different types of Greek letters. But the main one that we use for angle measurements is a theta. And like I said, we really try to do that because there's so many different variables that can happen because there's 3 sides and 3 angles, 6 functions. So to help kind of distinguish whether we're talking about sides and angles, then we kind of switch and we leave the English alphabet to the sides, and then the Greek alphabet will be labeled with the angles. So I typically use the theta. That's the easiest Greek letter to write. And that's typically what books use in definitions. So a lot of times we'll look at some definitions, and for angles they'll use that Greek letter theta. But I'm just trying to explain why we have that new letter in there. But we'll use that quite a bit for angles. Okay. So down here are the 6 trig functions that we're going to use, and next to it are the abbreviations. Most of them are pretty straightforward. So we have sine, which we abbreviate SIN to say sine, not sin. So again, it's talking about trig function, so it's sine. And then we have cosine, which just abbreviates the first 3 letters. So we do COS for cosine, and then tangent, TAN for tangent. Again, those are the 3 main ones, the ones that we've talked about in the past. Okay. Now each one of those has a reciprocal function, so it's kind of its opposite. So that's why I've kind of lined them up this way. Sine's reciprocal is the function cosecant. Okay. So if you see the abbreviation CSC, which this is the only one that's not a straightforward abbreviation, because if you look, cosecant's first 3 letters are the same thing as cosine, so they both couldn't just use the letter COS. So they use this combination of letters. We're talking about cosecant. Okay. Secant is the reciprocal of cosine, so it's its opposite, and it uses the abbreviation SEC. And then we have cotangent, which is the abbreviation of COT. That's the one that's really apparent for reciprocals of each other because they sound similar. So tangent and cotangent are reciprocals. The other ones, it just takes a little bit of getting used to which one's reciprocal of what. The biggest thing I always use is you always pair an S with a C for reciprocals. So for sine, its reciprocal is cosecant. Cosine, its reciprocal is secant. Okay? So like I said, we're used to the first 3. We've used those in the past, but the last 3 are the new ones that we'll talk about. And like I said, they're essentially just reciprocal functions. And so when we're writing our ratios, we kind of know what reciprocal means. So it's pretty straightforward how we get those 3 once we have the main 3 set up. So down at the bottom of that page, I already have the triangle labeled. Now again, the side that always remains the same no matter what is the hypotenuse. Okay, and I just abbreviated it because otherwise it would was labeling the triangle. So the hypotenuse is always across from the right angle, okay? Because it's always your largest side. So wherever you see your right angle, the side across from it is the hypotenuse. That's always the easiest side to label because that side never changes, okay? Now the other two sides depend on which angle we're talking about. So if you'll notice with each one of my triangles, I'll have an angle labeled because I have to tell you which angle we're talking about because whether the side is opposite or adjacent depends on which angle we're talking about. So I've labeled this bottom angle, and so that means the side across from that angle is the opposite, and then the side next to it is the adjacent, okay? So that's why you should always have an angle labeled somewhere in your triangle because the opposite and adjacent change depending on whether you're talking about this bottom angle or this top angle. So if I was talking about this top angle, the side across from it would then be its opposite and adjacent. So that's one thing you have to remember with right triangles is that hypotenuse always remains the same. It's always the side that's across from the right angle, but the opposite and adjacent change depending on which angle we're referencing. So that's why you should always see some sort of variable referencing that angle. Like I said, typically we use, now that we're in upper level math, we typically use Greek letters to reference angles. So that's where my theta is. So when you're writing out your ratios, we use the abbreviation SOHCAHTOA to help us figure out which sides and angles, or which sides correspond to which trig function. So the first letter, and this is just with the first three, so actually help me separate it out, because I know you guys have all this on your paper already, but to kind of help separate it out, we're just focused on the first three to start with. So the way the SOHCAHTOA device works, the S tells you which trig function you're working with, so that's sine. This would be cosine. This is tangent. So the first letter tells you which trig function we're referencing, and then the other two letters behind it tell you which sides are related to that trig function. So with sine, it's opposite and hypotenuse. So when we write it out as a ratio, the one thing you have to always remember is sine and cosine and tangent by itself is nothing. So it has to have an angle reference next to it. So if you notice with each one of my trig values, I have the theta there. That's referencing the angle that I have labeled from the triangle. So it's compared to this angle. So all your trig functions are expecting an angle. And right now we're not necessarily worried about finding that angle. Eventually we might, but right now we don't have numbers for our triangle. But again, we have to have some sort of angle measurement next to our trig function. So in all three of my ratios that I'm about to write, I have the theta that's referencing that angle of my triangle. So again, the way we write out our ratio is that sine equals opposite over hypotenuse. So when you see the two letters behind it, it's referencing how you write the ratio. The opposite side would go on top. The hypotenuse side goes on the bottom of the ratio. So then with cosine, it's adjacent over hypotenuse. The adjacent side goes on the top part of the ratio for cosine, and the hypotenuse goes on the bottom. And then for tangent, it's opposite over adjacent. So we actually end up using these ratios in several different contexts. But again, the big thing you have to remember is that each ratio has three different parts. An angle, actually technically four parts. It has a trig function, an angle, and two sides of the triangle. Okay? So whenever you're looking at one of the ratios for the trig values for the right triangles, you're actually looking at four different pieces of information. The specific trig function we're looking at, an angle, and two sides. Okay? So then, do the ratios for the new reciprocal function. What does that word usually mean for reciprocal? What do we usually do with that? If we're talking about a fraction. We flip that. Okay? So, it still means the same things. That's why the word reciprocal is going to be important for us. So when we set up our ratios, and again I did another reminder for what they're the reciprocals of. This is cosecant. It is the reciprocal of sine. So since sine is opposite over hypotenuse, what would the reciprocal of that be? Yep, h over o. So cosecant is hypotenuse over opposite. So like I said, they're three new functions, but they're very much related to our original three. Okay, so secant being the reciprocal of cosine, what would its ratio be? Yep, h over a. So we're just going to flip cosine. And then cotangent being the reciprocal of tangent, what would our ratio be for cotangent? So those are all 6 ratios for sine, cosine, tangent, cosecant, secant, and cotangent. So really the big reason why we still just use the label for SOHCAHTOA, because the cosecant, secant, and cotangent doesn't have their own, because once you know that cosecant's the reciprocal of sine, you just know that you can flip that. Okay? Secant's the reciprocal of cosine, you can flip it. There are 2 sides. Cotangent's the reciprocal of tangent, you can flip the 2 sides. So we still just use the SOHCAHTOA abbreviations to help us remember which goes with the main 3. And then once you know which goes with the main 3, you can find the other 3 pretty easily. Okay. So all we're going to work on today, we're not worried about finding sides, not finding angles yet. We're just going to be working with setting up the ratios. So just being able to work, making sure we're good to go with how each thing works together. So that's what we're going to do in the first few pages of notes, is you're going to be given either a triangle where you already know all 3 pieces, and so you just have to write the ratios, or sometimes you might just be given 2 sides, but we know from a past property, there's a way we can find the 3rd side if we're given 2 sides of a right triangle, which we'll talk about in a second. So again, we're not worried about finding exactly specific angles or sides. Well, in this case, we actually know all 3 sides. We're not worried about finding the angle. All I want you to do is write the exact trig values for each function. Okay? So the big thing I want to emphasize before we start doing the example is when you see that word exact in a direction, what that means is you're going to leave it as a fraction, because most of the time we'll end up working with kind of not so nice fractions. You may be able to simplify them a little bit, but whenever you say exact, I don't want the decimal, I don't want an approximation. So if we're working with a fraction, leave it as a fraction. Sometimes we're working with square roots because we end up having to use the Pythagorean theorem. If it's a square root that doesn't work out evenly, we leave it as a square root because that's more exact. Because if you leave it as a square root of 5, that's more exact than trying to get that decimal approximation. So the big thing to remember is the direction for these will always be find the exact trig values for all 6 functions. So we're going to leave them as fractions. If they're square roots, leave them as a square root. So you're just going to leave them as exact. Okay? So before I start labeling my 6 functions, I want to label the triangle so I know which side goes with what trig value. Alright, so the first side I always label is the hypotenuse, because that's the easiest one, because that one never moves. Which side would be the hypotenuse? The 65. Yep, it's always across from the right angle. It should also always be your biggest side. So there's my hypotenuse. And then I have to look to see, okay, which angle am I referencing, which I made it easy because I referenced the same angle from my slide before. But you do have to make sure you're careful, because you can't just label the opposite and adjacent right away. You have to make sure you look at what angle we're talking about. So since we're talking about this angle, the side opposite of it would be what? 33. And then that would make 56 my adjacent. So now I know what all 3 sides are labeled as based off of this angle. So now I'm going to write my 6 ratios. Alright, so sine. So what 2 values are we going to use as sine? Yep, so it's 33 over 65. What about cosine? 56 over 65. our main three. So sine was opposite over hypotenuse, cosine was adjacent over hypotenuse, and tangent was opposite over adjacent. Now notice, with each one of my trig functions, you have to make sure you keep that angle next to it. Because like I said, the sine and cosine and tangent are nothing without an angle. And right now we don't know what the angle is, so we're just going to use that little theta to show that the sine of our angle equals that. Cosine of our angle equals that. Tangent of our angle equals that. Like I said, each ratio has 4 bits of information. A certain trig function we're using an angle, which we don't know, so we have to use a theta, and 2 sides. Okay. So now that we have our main 3, now we're going to write our 3 new ones. We have cosecant. Get us used to our abbreviations. So CSE is cosecant, secant, and cotangent. So once you have the main 3, since these 3 are its reciprocals, we can kind of just look at those and reference that. So cosecant is the reciprocal of which one? Sine. So we're going to look at sine and do the reciprocal of that. So it's going to be 65 over 33. What is secant the reciprocal of? Cosine. So we're going to look at cosines and just flip that ratio, 65 over 36. And then what's the reciprocal for cotangent? Tangent. So we'll look at tangent ratio and flip that. And those are the exact trig ratios for all 6 functions. Questions about that first one? And that's essentially, like I said, where we're going to focus on now. There's a couple of different variations, so each one of my examples is a little bit different. This one was very straightforward because we had nice whole numbers, so we could just leave it as fractions. But like I said, since we're working with triangles, the possibility of working with the square root is always in play because, again, the way we find the missing side, if we don't know one of the 3 sides, is using the Pythagorean theorem, which is a squared plus b squared equals c squared. So when we have to solve for side, we often have to take the square root. So that's the big reminder I put up here. So we've used the Pythagorean theorem, I know, in the past. So whenever you're working with a right triangle, this only works for right triangles. If you're missing one of its sides, then you can use the Pythagorean theorem to help you find that missing side. Because if you notice on this triangle, I only have 2 sides labeled. Okay? What 2 sides do I know? Yeah, I know hypotenuse. This one's hypotenuse. I know because it's across from the right angle. So I know this triangle is situated a little bit different than my other 2. But again, you have to look where the right triangle is, or the right angle is. That's the hypotenuse. And then I also heard the other one, it's the adjacent. Because again, we're referencing this angle. So it's right next to that angle. So this is the adjacent. So we're missing our opposite. In the Pythagorean theorem, there's 3 places to put all 3 sides. There's only one value that has to be specific. Okay? You remember which side has to go in a specific spot? The C has to be hypotenuse. Yeah. Because the hypotenuse is always the biggest side, it has to be where C lies. Because that's the only way you can add 2 sides, square them, or take 2 sides, square them, add them together, and still equal something bigger. Okay? So the C has to be the hypotenuse. The A and B are actually pretty flexible because you're squaring them and adding them. So whether you treat the adjacent as A and the opposite as B, or the opposite is A and the adjacent is B, it really doesn't matter because since you're working with squares in addition, you can kind of, the order is a little fluid because whether you add a 2 plus 3 or 3 plus 2, it's always 5. Okay, so A and B can switch whichever one you want it to be, but C has to be the hypotenuse because it has to be the biggest side. Okay, so I picked this one specifically because this one's, if it's just regular numbers, it's pretty straightforward. You plug everything in, square it, do the square root. So I tried to pick an example that was a little bit tricky because if you look at what my hypotenuse is, is both a real number and a square root. So there's a certain thing we have to do with that. So they're not always going to look like this, but I did try to do an example where it's a little bit trickier, so that way we could go through one of those together because you are going to see those on some assignments. Alright, so I'm just going to treat adjacent as my A. So what I'm missing is the opposite, so I'm going to label that as B. So I have 6 squared plus B squared, leave that blank, equals 2 square root of 10, square that whole thing. So then I need to solve for B. Okay? Everyone with me? So 6 squared part is fine. That's 36. That's B squared because we don't know B is plus U. Okay? So when we get to something like this, there's actually 2 different things with that hypotenuse. There's a number in front and the square root. But like I said, we leave them as exact values. So whenever you see a square root that's not even, we just have to leave it. So that's why it's left as the square root of 10. So, but now we have to plug it into the Pythagorean theorem. So we have to square it. Okay? Most people can guess that if you square a square root, what happens? They're going to cancel out. But there's this extra number in front. So technically, you actually have to square both of those things. Okay? And since it's just being multiplied, you can do that. So make sure you square the number in front. So what's 2 squared? 4. And then technically what was happening here is multiplication. So I'm going to continue that multiplication down here. So now I'm going to square the square root. So if I take the square root of 10 and square it, what's that going to be? 10. Yep, because the square root and the square are going to cancel out, so you'll just have the number in front of it. But the big thing to remember is that if you have an additional number in front of the square root, make sure you square that as well. And so then we're going to multiply that together. So we'll get 36 plus B squared equals 4. Does that make sense? Like I said, most of the time you just have a number or a square root. That's pretty straightforward. So I wanted to do one where it combined the two because that's something we really haven't worked with yet. So I wanted to go through that one together so that way when you see it on your own, you can kind of have a little bit of idea what you're going to do. Okay? So then we just need to finish solving for B. So I'm going to subtract the 36 over here. So what's 40 minus 36? 4. And so then how do we get rid of that squared? Square root it. So what's my B? 2. Okay? So that means my opposite is 2. So now I know all 3 sides, so I can write all 6 ratios. There's another thing that's a little weird when it comes to square roots. Okay. I want to skip these for right now. So usually I do those first. Why don't we go to the tangent? Okay. So a tangent, what 2 values do we use for tangent? Yep, adjacent and opposite. So we do 2, it's going to be 2 over 6 because it's so. So tangent is opposite over adjacent. So it's 2 over 6. Now, if you look at that fraction, we can simplify that. That's going to be 1/3. So again, we're leaving them as fractions. So don't turn it into a decimal, but leave it as a fraction. Let's see. Okay, I'll go back and do sign now. Sign just gets a little weird because there's another property when we talk about trig where square roots are involved. It makes it a little goofy. And then this particular one is goofy because, again, it's a number and square root. Okay, so I'll come back and do the other one in a second. So sine is opposite over hypotenuse. So it's going to be that 2 over 2 square root of 10. Okay. First thing I notice is there's a 2 here and a 2 there. So I can simplify that. Again, we're dividing. So what can I simplify that to? 1. Yep, so just 1. So you have to leave the square root of 10 on the bottom because that's where it was originally. But again, divide those out. So it's 1. You could technically write the 1 in front of the square root of 10, but you don't necessarily have to. Okay, so here's the other goofy property that happens when we are working with a square root. Okay, me 1 second. I didn't make myself a mistake, so I'm just going to rewrite this real quick. Okay. So, are you ready? The other goofy thing with trig functions is we don't like square roots on the bottom of a fraction. It's just not as simple because the square roots down there, a lot of goofy things can happen. Don't really know why, but this is just what we do in math, okay? So with the square root of 10 being down there, we don't like that. So we do something called rationalizing the denominator or simplifying the fraction so we can get the square root out, okay? Essentially what we can do is one thing I know about square roots is if you take like the square root of 2 times the square root of 2, that becomes the square root of 4, which makes it just 2. So what the property that we can use with square roots, if we want to get rid of the square root, is if you multiply the square root times itself, we actually end up getting rid of the square root. So what we do to rationalize this denominator is we're going to multiply whatever that square root is. Just multiply it by itself, okay? Because when you do that, if you take the square root of 10 times the square root of 10, since they're both square roots, you can multiply the numbers together. So what's 10 times 10? 100, and then you take the square root of that. So what's the square root of 100? 10. Okay, so essentially why I can pick the square root of 10 to get rid of the square root of 10 on the bottom is if I multiply these two things together, and it ends up just being the number 10. Okay, so the square root of 10 times the square root of 10 becomes the square root of 100. Is it okay that I didn't write the square root of 100? Does everyone understand where it's coming from? So then essentially, then we square root the 100 and it becomes 10. Now it is a fraction, so you suppose I can just multiply it to the bottom of the fraction? No. So the reason why I use that square root of 10 is to get rid of the square root from the bottom. So now it's just 10, but I have to take that same thing and multiply it to the top. Okay? And so then what's 1 times the square root of 10? So essentially, when you have to fix something that has a square root on the bottom, it actually just move the square root up on top and then take the square root off the number. Okay? That's essentially what happens each time. So once you get good at it, you may not necessarily have to show this middle step each time. I probably will, just so you can see the progression. But that's the other goofy thing with exact values, is that we don't want that square root on the bottom, but we want to leave it as a square root. So you multiply the top and bottom by the square root to get rid of the square root on the bottom. Okay. Then cosine is adjacent over hypotenuse. So 6 over 2 square root of 10. So I can simplify first. So again, I can divide these two numbers that are in the square root. What's that going to make? 3. Yep. So the square root of 10 still has to be on the bottom for now. And now we want to get rid of the square root of 10 off the bottom. So what do I multiply by it? Yep, the same thing. But I have to multiply it to the top and bottom of my fraction. So what's the bottom of the fraction going to be? 10. Yep. Now with this one, 3 times the square root of 10. This one, the 3 doesn't have a square root, and the 10 does. So just like here, notice there's a real number and a square root here. You can't actually multiply these two numbers together. So it's going to end up looking like this, 2 square root of 10. So it'd be 3 square root of 10 on the top. There's cosine. Like I said, I promise not all of them are like this. I just really wanted to do a challenging one together. So that way, when you see the 1 or 2 that you might have, you can do it. But most of them are straightforward, like the first one. So then, now we're going to write the reciprocals. So we got cosecant. It's the reciprocal of sine. Now here's the trick I use. You could go ahead and use the ending of sine, the square root of 10 over 10. But if you flip that, the square root's on the bottom again, and then you have to mess with it again. So what I do, that's why I always write the original one, because I'm just going to go back to the original one and flip it, because that's a lot easier to work with than having to worry about the square root on the bottom again. Does that make sense? So I'm going to take the original sine, which is flipping opposite over hypotenuse. So I'm going to do hypotenuse over opposite. So it'd be 2 square root of 10 over 2. And again, the reason why I do that is I try as much as I can not mess with the square roots on the bottom, because it gets a little goofy if you do that. But with this one, the square root isn't on the bottom, but I can simplify that a little bit. What's that going to become? Yep, square root of 10 over 1, or you won't necessarily have to write over the 1, but I did here. What secant the reciprocal of? Cosine, okay? So again, instead of using this ending result for cosine that I have, I'm going to go back to the original one, because cosine is adjacent over hypotenuse. So that means secant is hypotenuse over adjacent. So I'm just going to do this 2 square root of 10 over 6. And then can I simplify that one a little bit? Yep. So I'm going to make it square root of 10 over 3. And then this one, what's cotangent the reciprocal of? Tangent. So tangent is opposite over adjacent. So cotangent is adjacent over opposite. So it's 6 over 2, which can I simplify that one? So then there's one. This one got a little long because there's some goofy things. There's all 6 values. Okay, we're gonna do one more. This essentially, you can be given the information without having the triangle. So if I give you one of the trig functions, I actually have given you 2 sides. And we can use the Pythagorean theorem to find the third side, and then I can write the rest of the ratios. So you don't necessarily have to draw the triangle from this. So a sine, what 2 sides does sine have? Opposite and hypotenuse. Yep. So that means this 1 is my opposite, and this 3 is my hypotenuse. So what am I missing? Adjacent, okay? So we can use our Pythagorean theorem to help find that missing side, okay? So we're looking for adjacent, so I'm going to leave that as A. So then I can put my opposite into B, 1 squared equals my hypotenuse, because it has to be C. And then solve this out so I can get my adjacent side, so then I can write the rest of the ratios. So what's 1 squared? 1 plus 3 squared? 9. Okay, so I subtract 1. So I have a squared is equal to 8, square root of 8. Does 8 have a nice square root? No, so we're just going to leave it. Okay, so again, we're looking for exact values. So if it doesn't square root evenly, everybody with me? Leave it as a square root. So now I'm going to write the rest of the ratios. I already have sine, so I'm going to start with cosine. What 2 sides does cosine use? Yep, adjacent hypotenuse. So I have opposite, adjacent. This is not, or opposite hypotenuse. This is not my adjacent. There's my adjacent side. So I'm going to do the square root of 8 over 3. There's cosine. So what 2 sides does tangent use?
Opposite and adjacent.
Opposite and adjacent. When I wrote that, I wrote the H from that. Okay. So we have my opposite is 1. My adjacent's at square root of 8. Do I like the square root of 8 on the bottom? No. So I'm going to fix that. So what do I multiply it by?
Square root of 8.
Square root of 8. So I have the square root of 8 over 8. Like I said, essentially what happens with that each time is the square root moves up top with the number, and then the bottom number is the number without the square root. Okay, so there's tangent. I wrote secant. What's secant the reciprocal of? Cosine. Yep, I switched it over. Usually write cosecant next, but I wrote secant. So it's going to be the reciprocal of cosine. So we're going to flip cosine because it's a hypotenuse over adjacent. I did that on purpose because then with this one, do we like the square root of 8 on the bottom? Nope. usually when you're working with this, there are two, if you're working with the square roots, that you have to fix. Okay, the other ones should be fairly straightforward. But like I said, typically when you're working with this, there should only be two that you have a square root on the bottom. All the rest of them shouldn't be. Okay, so then let's go back and do cosecant. What's cosecant the reciprocal of? Sine. Okay, sine's the one I was given, so what's the reciprocal of sine? 3/1. And then finally cotangent. It's the reciprocal of tangent, so I need to do adjacent over opposite. What's my adjacent? Square root of 8. What was my opposite?
1.
Now with these, would I have necessarily had to put the over 1 part?
No.
That's it for today.